Advantage of the nearest neighbor model. It's absolutely seamless. It's absolutely seamless to do multi-class. Okay, so now I'm showing you the digits data in all its glory. So, you know, you have zeros, 1s, 2s, 3s, 4s, and so on with different symbols. And you see in the average intensity symmetry space, it's actually quite a mess. Okay, but that just means that, you know, it's hard to classify in this space and you might need other features. Now, how can we extend the nearest neighbor to multi-class? Well, you know, we just, okay, if we're doing nearest neighbor, you find your nearest neighbor and classify according to that class. Okay, and if you're doing k-nearest neighbor, you find your k-nearest neighbors and classify according to the majority class in your k-nearest neighbors. Okay, and so with respect to average intensity and symmetry features, you know, we can see what parts of your input space get classified as what digits. And here is the nearest neighbor classifier extended to multi-class. Now we might be able to do better with k-nearest neighbor, okay, but you know, we can see all the things that we expected to see. So, you know, 0 is this region with, you know, pretty high average intensity and a pretty high symmetry. Okay, this whole region here. Okay, 7 has not much symmetry, okay, and not much intensity. 1 has a lot of symmetry, but not much intensity. 9, 8, 3, you know, 6, 2, and so on. Okay, what a beautiful classification. What a beautiful separation of your space into regions that correspond to 0, 1, 2, and this is all created by the nearest neighbor algorithm seamlessly. We can do multi-class. Okay, and when you do multi-class, so this is about all we're going to say about multi-class. When you do multi-class, you know, there's what's called, you know, the confusion matrix. Okay, and you can compute the confusion matrix in the training, and you can also compute it in the test. And here's the test confusion matrix. Okay, and what that does is it says, you know, there are all the data points have a true class, 0, 1, 2, 3, and so on up to 9, and you predict a certain class, 0, 1, 2, 3, up to 9. So if the true class is 0, and you predict 0, you got it right. Okay, everything else is wrong. Okay, and so what you can see is that in the data, 16.5% of the data is 0. So 0 is a very popular digit, and so on and so forth. And, you know, we can see that, you know, one of the digits that the nearest neighbor classifier is making the biggest mistake on is the 3. It's only getting, you know, 2% of those correct. A lot of mistakes. Okay, and we see that the 3 is getting confused with the 0. So many 3s are classified as 0s. Many are classified as 9s. Okay, here's an interesting one, the 4. Okay, the 4 is also quite low in accuracy, and many of these 4s are classified as 9s. And you can see why. Look at the 9 versus the 4. They look very similar. So the nearest neighbor algorithm with respect to symmetry and intensity is going to make a mistake between 4 and 9. So this confusion matrix tells you what's classified as what. In other words, where is the confusion occurring? And sometimes you can look at the confusion matrix in sample and try to, you know, improve the algorithm. Okay, if you look at the classification accuracy, that's the sum of the diagonals, it's 41%. And you might look at this and say, a mere 41%? Yes, we certainly can try to get this higher, okay, by, you know, improving the features, getting more useful features, and so on and so forth, moving up to k-nearest neighbor. But this 41% is actually quite good when you think of this as a 10-class problem. So a random classifier, for example, which classifies into a random class, will only have a 10% accuracy. So this is 4 times better than, you know, a random classifier. And it's only based on average intensity and symmetry. And you can see when you look at this that it's a mess. So optimal is going to be close to 41% accuracy. And, you know, it's not going to be very good. And that has to do with the fact that we need better features and perhaps more features that can allow us to separate this data. Okay. But, you know, we are just building the theory and testing it. And so, you know, 2 features is more than enough to see what's going on, to play around. Okay. And now let me summarize the nearest neighbor model. It's a very powerful model. So let me start with what's great about the nearest neighbor model. It's simple. Wow. You can explain it to a 5-year-old. In fact, it's what the 5-year-old uses probably. No training. Okay. Near optimal E out, especially with, you know, a suitable choice of k, for example, k equals 3 or k equals square root of n, and enough data. Okay. And something I didn't mention yet is that, you know, a lot of times when you have a client and then the client gives you the test point and you say, here, this is what I think, the client is going to ask you, why? Can you justify your decision to me? Especially in sensitive applications like credit approval. So, you know, here's a client and you denied credit. Why? Tell me why, because I need to be able to justify that to the client. Well, with the nearest neighbor algorithm, it's so easy to justify. You know, because you classify it on the basis of a nearest neighbor or k nearest neighbors. So you just take the nearest neighbor and say, here, this person is close to that person, and that person was denied credit, and this is why I denied him credit. Ironclad justification. The data says that you should deny people like this, and this is a person like that. Can easily do multi-class. These are all fantastic pluses. Seamless to do multi-class. Okay. Can easily adapt to regression or logistic regression. Regression, instead of taking the sign of the average, so currently for k nearest neighbor, we take the sign of the sum. Well, instead of doing that, you just take the average of the y values. Okay. For logistic regression, you count up the number of y values that are plus 1 in your k nearest neighbors and divide by k. So compute the fraction of plus 1s. That gives you a probability. Okay. So 1, 2, 3, 4, 5, 6 fantastic pluses. There's only one small minus in those 6 pluses, which is the near optimal E out. Well, it needs sufficiently large n, and in practice you have a fixed n. And that brings all the other models into play, especially the linear model. Because once you fix n, you've got to play around with overfitting and so on and so forth. Okay. And there's one other big minus of the nearest neighbor, okay, which is probably why it's not so popular in practice. Which is it is computationally demanding. For a start, you have to keep all the data. So imagine you have 1 million data points and they're million dimensional. Wow, the memory alone is 10 to the 12th, order of 10 to the 12th. Okay, so it's computationally demanding. Then, when it's time to deploy, okay, and you have 1 million data points in 1 million dimensions, just to classify a test point, you need to compute the distance to all those million data points. So it's computationally demanding just to even compute the output on a test point. So we're going to address those two issues next. Okay, but for the moment, leaving you with this miraculous model which can obtain close to the out-of-sample error. And this is an example of a prototypical non-parametric model, and such non-parametric models typically have that feature that, with n large enough, you can get close to optimal performance. It's just that in practice you have fixed n. Okay, so that brings the other models into play. But wow, what a model, what a miracle of the day. Checking out. See you next time.